So it's visible.
It's properly audible. Oh, okay. Okay. So, hello everyone. Welcome to this 10th class on electromagnetic theory. Huh. So, in the last few classes, so we had started with electrostatics and then magnetostatics, and then we derived all the different Maxwell's equations, and we moved to electromagnetic waves, and we saw how one can use the Maxwell's equations to study propagation, reflection of electromagnetic waves, and all that as it moves from one medium to another. What are the different boundary conditions? Okay, and then in the last two classes, we have been talking about transmission lines. So where we started with, understanding lumped circuit and distributed circuits as to see where the effect of transmission lines become important, okay, based on the dimensions of your transmission lines and the wavelength of the signal that we are talking about. We saw that like if they're comparable, there's a range where the connecting leads or the transmission lines can play a very important role, and uh, the voltages or the currents, they change as we as they transmit along the you know transmission lines. So there are conditions of impedance matching and looking at how the reflection coefficients are, or how the standing wave ratio is. So based on that, you can design your circuits by choosing proper impedances, matching them, so that you get less distortion in the signal, okay, and less attenuation or lossless conditions and all that. So we discussed about all those. And then in the last class, we have been talking about Smith charts, where we saw that graphically how one can calculate or first how one can represent impedances normalized to the characteristic impedance of your transmission line, and then from there graphically how one can calculate how these impedances are changing as we move towards the generator or away from the generator towards the load and all that, and from there get an idea about what the standing wave ratio is, how what should be the proper, if we want to add a stub for impedance matching, you can have stub, and then when you're adding a stub, what should be the length of the stub and how far should it be from the load and all that. So all this can be evaluated graphically by using the Smith chart, and that's what we had discussed in the last class. So in today's class, we would slightly change gear and move towards waveguides. So we would first start with seeing that how different are waveguides from typical transmission lines, okay, and then we would see that what are the different characteristics that define the properties of a waveguide. So a waveguide, as you can understand, it guides the wave, right? The wave propagates through a waveguide, and it's more, you can say, so if properly designed, it can give you controlled electromagnetic modes, like which modes do you want to transmit or which one do you don't want to transmit, or based on that, so you can design your waveguides accordingly, and that can be used for proper transmission of EM waves. And we would start with seeing how different they are from typical transmission lines, and then we would talk about how the Maxwell's equations change when we are talking about EM waves inside uh, a waveguide. what are the different conditions, what defines the different modes that a waveguide supports. Okay, and we'll try to solve some basic questions that come along the way. And then we would briefly discuss also about what happens when you have a pulse, you know, like if there's a pulse that is transmitting along a transmission line, what happens there? Okay, how the width of the pulse and the length of the transmission line, how are they correlated? What are the different conditions based on which one should design the transmission lines for digital signals, where you're talking about very fast signals, very short pulses. Okay, so all those kind of discussions will have in our class today. Okay, so let's get started. So first, let us look at how transmission lines are different from waveguides. So as we saw in the last class, or the last to last class, transmission line is normally, this is how it looks like, right? You have two conductors, something like this. Okay, and then there'll be some source or generator at one end, and then there'll be currents flowing through the circuit. You would have some load at the other end. So this load can be a resistive load, or it can have capacitance and inductances, so it can be a impedance. Okay, and then basically there can be reactive loads as well. And then this is how a circuit completes. And so basically there is a positive terminal and a negative terminal. There are two conductors involved, and the current is flowing through them. So as the current flows through these wires, you have associated inductances, right? And because you have two such positive and negative uh, terminals, and then you have two conductors, so there can be a capacitor between these two. Okay, and no wire has zero resistance, so they can have some finite resistance. And if there is some resistance in parallel, it can be considered as some conductances. So that gave us the idea of the distributed circuit parameters. Okay, and this is how typically it looks like. So a transmission line comprises two conductors, and typically they work in the range of few gigahertz quite well. And then the important point is that we know that in free space you have this transverse electromagnetic waves, and transverse electromagnetic waves are also supported in the transmission lines. What do you mean by transverse electromagnetic wave? So as you can understand, transverse means perpendicular. So the electric and the magnetic fields are perpendicular to the direction of propagation of your wave. Okay, that's why typically that's typically true when we talk about also transmission in free space, right? The electric and the magnetic fields are perpendicular to the direction of propagation, and that's the TEM mode, and that is supported in a transmission line. Okay, but then how does the waveguide differ from a transmission line? So now consider the situation where you have just one conductor, okay, not two. So in coaxial cables, suppose there you have two conductors, right? And you can also have dielectrics in between. But here we're talking about just suppose some conductor, okay? This is some conductor and a hollow pipe like thing. So a hollow pipe with a conducting surface. So that can serve as a waveguide, okay? So it comprises of one conductor, and typically it can support much higher frequencies till terahertz. And then what we will see. Okay. Okay, so what we are currently trying to do is we are trying to look at how transmission lines are different from waveguides. So one of the major differences between transmission line and waveguide is that transmission line comprises of two conductors, where for waveguides we have one conductor. Okay, and we will see that in a waveguide, TEM modes are not supported. Okay, we can have different higher order modes. We can have transverse electric mode or transverse magnetic mode. What do we mean by that? Why are the TEM modes not supported? That's something we'll just be discussing in the coming slide. But that's how it's different from a typical transmission line. Okay. So to start with, if we have to, start from the Maxwell's equations, so we can say that this is how a typical waveguide will look like. Okay. So you have it's like a hollow pipe with a conducting surface. So suppose this is a metal. Okay. So then we know that for a perfect conductor, the electric field and the magnetic field, they should be zero when we talk about this inner wall, right? Now that sets the boundary condition for the waveguide. Okay. So in free space, we know that we have this transverse electromagnetic waves where the electric and the magnetic fields are mutually perpendicular to each other and also perpendicular to the direction of propagation of your wave. And in a typical free space, we don't have any such boundary conditions, right? But now because you have this waveguide, which restricts or puts a boundary condition, which says that at this inner wall, the electric and the magnetic field components, like this comes from the Maxwell's equation itself, that the parallel components of electric field and the transverse components of magnetic field should go to zero when we talk about the inner surface. Okay. Now, if we look at the Maxwell's equations, this is how it will look like. So if you consider no, free charge, like no rho and no current sources, so then J is zero. So in that case, this is how the Maxwell's equations would look like, right? Now here we will work out the solutions for the Maxwell's equations, considering that suppose there is some monochromatic wave that is propagating through this hollow tube. Okay. So a typical monochromatic wave would take up a form something like this, right? So if you consider that the wave is propagating along Z, okay, so this is X, this is Y. So consider that the hollow pipe runs along Z and the wave is propagating along Z. So in that case, a typical monochromatic wave would have the electric and the magnetic fields with this generic form, right? So E naught e to the power I kz minus omega t, and then B naught e to the power I kz minus omega t. So here Z shows that it's propagating along the Z direction, right? So now if we consider this E and B, these are vector quantities, right? So they can have components in all the three directions. So you can write it as Ex x cap plus Ey j cap plus Ez k cap. Similarly, you can write B as Bx x cap plus By j cap plus Bz k cap, right? Now, there can be different conditions as we will be able to see. So normally when we say transverse electromagnetic wave, that means if the wave is propagating along Z, then there should be no component of electric field along Z. That means Ez should go to zero. And then there should be no component of magnetic field along the propagating direction. So Bz should be zero. So that's our typical TEM wave. Okay. What we will see is that if Ez and Bz both goes to zero, there'll be no solution when we talk about waveguides. Okay, so in waveguides, we have situations where either Ez is zero, but Bz is non-zero, then it becomes a transverse electric wave, or you can have condition where Bz is zero, but Ez is not zero. So then it becomes a transverse magnetic wave. Okay, and we'll see why these conditions arise. So what we can do is if we start with this Maxwell's equations, okay, and then we try explicitly write the equations in terms of the different components, okay, Ex, Ey, Ez and Bx, By, Bz, this is what we will be getting, right? So here we have used the curl operator on the individual components, and because you have del B, del T, and the temporal change is given as this I omega T term, so you have this I omega coming in here, right? Similarly, for the magnetic field, you would have an expression like this. Okay, so these 6 equations that you can see comes from the third and the fourth Maxwell's equations. Okay. Now, what you can do is using this, you can actually solve for Ex, Ey, Bx, and By. Okay. So if you solve for that, what do you get? You get Ex, Ey, Bx, and By in terms of Ez and Bz. So that means if you can find Ez and Bz, you can actually find Ex, Ey, Bx, and By, right? And Now, if we consider the case of a typical TEM wave where EX and BX both are zero, what would happen? So all of this would end up being zero, right? So there'll be no wave, right? So that's how it tells us that TEM waves cannot occur in a hollow waveguide. Okay. So rather now what we'll consider is a situation where we have some EZ or some BZ. Okay. So now these are the four equations which tells us that if we know Ez and Bz, we can actually find all the four other components. Okay. Now, how do we find Ez and Bz? So what you can do is you can now use these expressions in the first two Maxwell's equations. Okay. So what would happen? You would have all terms either in the term of like uh, as a function of Ez, or you would have something as a function of Bz. So there'll be two uncoupled equations, one for Ez and one for Bz, which would look like this, right? So now you can try to solve for Ez and Bz from here. And once you know Ez and Bz, you can actually find all the other components, right? So now let us look at typical cases, okay? So one of the case could be where it's a transverse electric wave. That means there is no component of electric field in the direction of propagation of your wave. Okay. So Ez is zero. That's what it means, right? But you need to have Bz non-zero in that case in order to get some wave, some solution to the equations. So you consider that your Bz normally has a form given as a product of like two functions, independent functions of x and y. So the typical way of solving, so if you remember how we solved for the Laplace equations long back, we'll use a similar kind of approach. Okay. So you write Bz as a product of x and y, where x is a function of small x and y is a function of small y. Okay. So now if you use this form and rewrite, so basically what we are rewriting is this equation, right? This is already zero. We know Ez is zero for TE waves. So we are using this, okay? And we are writing Bz as x, y, and then we are doing all this partial derivatives. So it takes up a form like that, and now we can use our well-known set of variables to get this individual partial differential equations, right? So this is only dependent on x, this is only dependent on y. So from here you can find this capital X, and from here you can find capital Y, right? And here, from our definition of wave vector, we know that if the different components of the wave vector are kx, ky, kz, so in our case, because the wave is propagating along z, your kz can be just written as, omega by c, okay? And then you have some component kx and ky, so it would take up a form like this, right? So this is directly just by using the, definition of the magnitude of your wave vector. Okay. Now, from here, by looking at this equation 1, you can consider that the general form of solution for x will be something like this. And here you have to now apply your boundary conditions. Okay. So the boundary conditions are given by this relation here, right? So B perpendicular should go to 0 and E parallel should go to 0. So here we are talking about the magnetic, if you are looking at this condition, this is telling us that Bx and By similarly should go to 0. Okay. Now, if we look at the expression of Bx, okay, how does it look like? So this is your expression of Bx, right? Now here Ez is 0. So this term is not there. So what you have is a partial derivative of Bz with respect to x, right? So that means you have a term which involves ddx of capital X, right? Now, in order to have Vx going to 0 at x equal to 0 and x equal to a, considering that you have this kind of a rectangular waveguide where there's some particular dimensions. Okay, so the dimension along x is a and the dimension along y is b. So the magnetic field should, like Vx should go to 0 at a equal to x equal to 0 and at x equal to a. So if you apply that condition, you get some possible values of kx, right? So this is given as m pi by a. Okay. Now the same thing you can apply for along y. Okay. And you would get another like possible values of ky, which is given as n pi by b. So from here, now you know how your expression of bz should look like, right? So bz, which is some product of x and y, where x is a function of small x, y is a function of small y, will take up a form something like this. So you can understand this depends on the dimensions of your waveguide. Okay, the value of a and b is important, right? Now, these are like all possible values of m and n, which given by like from starting from 0, like you can have all different combinations, and that would give you the different modes that are possible, right? So for each mn value, you would call this as a TEMN mode. Okay, so here m corresponds to the index for the larger dimension. So for this case, we have considered a to be larger than b. Okay. Now, what you can do, what is the smallest value that one can have? So smallest value of, okay, so before that, let us first write the expression for the wave number. So what you can do is basically, if you want to write an expression for the wave number, you can just put in the value of kx and ky, right? And use this relation, basically the definition of the magnitude of wave number. Okay, so that would give you k. Okay, now this term here is an important term because when omega is nothing but your frequency, right? So when omega is less than this term, what happens? The term inside here becomes a negative quantity. So basically, you get an imaginary value of k. What happens when you have an imaginary k? So if you go back to the earlier expression of electric and magnetic fields, so here if you put k as an imaginary quantity, you would get an exponentially decaying function, right? Because you would have k would have some I there, right? So I square you'll have a minus 1. So basically you will get an exponentially decaying wave, right? So what is it telling you? That when this condition holds, so when the frequency is lower than some value, then the waves become attenuated. So we cannot have propagation of such waves. Okay. So that sets the limit, the lower limit to the frequencies that can propagate through a given waveguide. Okay. So that is called our cutoff frequency. Okay. You can write it as omega mn. Now, what is the lowest cutoff frequency? So for lowest value, what you can have, so if you put, based on this, right, you can use this expression and you can think that if A is much great, not much, but if A is greater than B, right? So if you put both to be 0, m0, n0, this term would go to 0. So then there'll be no propagation. So that makes no sense, right? So one of them has to be non-zero. Now, which one will you put non-zero and the smallest non-zero value as like the integer to be 1? So something has to be 1, something has to be 0, right? Between m and n. Now, based on the dimensions, if A is larger than B, if you put m as 1, you would get a smaller value, right? So that tells us the lowest cutoff frequency that is possible for a waveguide, okay? For the case of a TE wave, okay? So TE10 is the lowest cutoff possible. And the typical cutoff frequency would be given as C pi and then put m equal to 1, n equal to 0. So C pi by A. Okay. So here A corresponds to the dimension, the larger dimension. Okay. So anything below this will not propagate because then your K will become imaginary and you would have attenuated waves. Okay. So they'll be exponentially decaying. So that sets your cutoff frequency. Okay. And this is the general expression of cutoffs for typical values of m and n. Now, you can define the wave number, okay, in terms of the cutoff frequency. So if you just replace the expression of cutoff frequency here, this is how the wave number would look like. From there, you can define an expression for the wave velocity, which is nothing but omega by k. Okay. And this term would be greater than c, but that doesn't matter because the energy propagates with the speed of the group velocity. Here, this is just the wave velocity, right? So if you calculate the group velocity, it would be given as d omega dk, and that will always be smaller than c. So everything is consistent, okay? So these are the different ways of defining your wave number, wave velocity, group velocity, and so on. So once you know your, what mode you're talking about, or what are the dimensions of your waveguide, you know whether the particular mode will propagate or it will get attenuated, and if it is propagating, what should be the velocity. All of that you can calculate, right? Now there's also another way of looking at it. So what you can basically do is you can, like, visualize this very idea of different modes propagating in a waveguide by considering electromagnetic waves that are passing through some pipe, some hollow pipe, and they're getting reflected on the surfaces. Okay, so you are having reflection as it hits the surfaces. Okay, so total internal reflection condition. And when they reflect, because they'll be having multiple reflections, and there'll be standing waves that would get formed. And the typical wavelengths of the standing waves will obviously be governed by the dimensions of your waveguide, right? So different standing wave patterns with the possible wavelengths given as 2a by m, and like lambda y given as 2b by n. This would be the typical wave numbers that would be possible. And so from there, you can again redefine and write the typical values of, propagation vectors. So these are the different possible wave vectors that the EM waves can have inside your electromagnetic, like this rectangular waveguide. Okay. And once you know the expression of your wave number or the propagation vector, so you can define the frequency from here. Again, you can get this expression. So see, this is your expression of your, the cutoff frequency. And then what you can basically say, so what is the wave vector? Wave vector gives you the wave number, and it tells you the direction of propagation of your wave, right? So that means from here, you can get an idea about what are the different angles which will lead to some allowed standing wave patterns. Okay. So basically, if your waves are starting at different angles here, what are the possible angles that would result in some net standing wave patterns? Okay. What are the values of theta? So you can just find. So if you take this as your right angle triangle, so this is your the kz component, which is given as k, and then you have the net magnitude, okay, which is given as the magnitude of k prime. So from here you get an expression of cos theta, right? So while your wave is propagating, if you want to find the net velocity along the waveguide, that would be along z. So you have to take a cos theta component. So if you take c cos theta, that would again give you the same expression of, group velocity as you had found here. So basically, it's just another way of looking at it, that you can either look at it from the very well-known idea of, Maxwell's equations and solving the wave equations, or you can just directly consider that you have some wave and then they are having multiple reflections, and from there get an idea about what are the possible angles which would be supported by the waveguide. Okay. So what we have understood so far is that for a, given mode, that is a given value of m and n, you have a cutoff, okay, which is given as this expression here. So here omega, so in questions when you have frequency in terms of hertz, you have to basically just use this relation. Okay, so this is in radian per second, and just be careful about the units. Okay, now this very well tells you that the cutoff frequency depends on the dimensions of your waveguide, but it also depends on one more factor. What is that? That is c, right? The c is nothing but the velocity of your wave, right? So when you're talking about free space, you have c, but if you have some other material, suppose the medium inside is some dielectric with some net permeability or permittivity, then the velocity would change, right? So in a more general case, you would have this root over of mu epsilon here, right? Where mu is the permeability, the permeability of medium, and epsilon is the permittivity. Okay. So that means the medium that is there inside the waveguide is also important because that governs the speed of the net speed of the propagation of the wave. Okay. So the cutoff frequencies depend on the dimensions and the medium that is there inside the waveguide. Okay, be careful about that. Okay, so that was about TE waves. Now you can also have TM waves, right? So what do you mean by TM? Transverse magnetic. So that means now your BZ has to go to 0, while your EZ is non-zero, right? So again, if we apply the same process, so we take EZ to be some function which is a product of two functions x and y. Okay, and again x can in general have a form something like this, and you would have boundary conditions. Okay, now the boundary conditions would be based on again this relation here, right? So for BZ we looked at this, like the relation, the second relation. Here we would look at the first relation. So that is telling you that E parallel should go to 0. That means EZ should go to 0, right? Now, what is, so if EZ goes to 0, so now that, directly tells you that your X should go to 0. So that's how it's different, right? In the TE mode, we had dx, like ddx of X going to 0, right? But here we don't have the derivative, okay? So here X goes to 0, okay? At 0 and at X equal to A. And similarly, by using this relation, you would get the possible values of kx. Okay. Again, you can do the same for y. Y goes to 0. So you would have again possible values of ky, and it would take up a form like this. So here you can see for TEM modes, you have this product of sinusoidal functions, right? Here you had cosine terms. Okay, that's because of that derivative in the boundary condition. Now, here, what can be the smallest value? So in the last case, what we had is we had m equal to 1, n equal to 0. That was our smallest, or the lowest, cutoff frequency, right? But here, if we put any one of them going to 0, this term would go to 0 because you have sinusoid functions involved, right? So the smallest possible value of n and m starts from 1. Okay. So if you want to find the lowest TM frequency, you have to put m equal to 1, n equal to 1, right? Rest remains the same. The expression of the cutoff frequency remains the same, but the lowest cutoff changes because you have sinusoidal functions. Okay. So the lowest cutoff here would be omega 1, 1. So you put m and n equal to 1. So this is how it would look like. Okay. Other expressions remain the same. So if you have to find the ratio of lowest TM frequency to lowest TE frequency, this is how it would look like. Okay, again, it depends on the dimensions of your waveguide. Okay. So now based on this, there can be very direct, very standard questions, quite simple, which just uses this relations and this equations. So we will try to solve some of them. So one such question from I think last year's assignment, there was some question like this, which said that you have this airfield 5 by 2 centimeter waveguide where EZ has a form like this. Okay, at 15 gigahertz, what mode is being propagated? That's the question, right? So now, first let us look at what are the different informations that are already provided to us. Okay, so here 5 by 2, that means the dimensions of the waveguide are given. So A and B is provided, right? Now you have the expression of EZ. Okay, and you have this. So EZ is a non-zero quantity, which is anyway telling you that it's a transverse magnetic mode that we are talking about, right? Now, if we compare this form with this form, right? And we know A and B. we can directly find the value of M and N, right? Just by comparing this with this, putting the value of A and B, right? So in that way, you can actually find what is the mode that we are talking about, right? Basically, that's how these are very standard questions. You can try to solve this kind of questions. Okay. Now, there's another question which says that you have a rectangular waveguide for which A is equal to 2B. So that means if you know A, you can find B and vice versa, right? And the cutoff frequency for TE02 mode is 12 gigahertz. Okay. What is the cutoff frequency for TM11? Okay. So what we have to do, we know the equation for, so see, it's in hertz, right? So we have to use this relation basically, right? This is your expression for cutoff. Now, based on whatever mode we are talking about, we'll put the value of M and N, and we know the relation of A and B with each other. So if we find one, we can find the other. And from there, we can use the equation. So directly by using this equation, we can calculate this kind of cutoff frequencies, right? So here, what would happen is, it would be something like this, right? So for the first case, you have A equal to 2B. So you can put A equal to 2B. And it's so the first mode, like TE02, so M equal to 0, N equal to 2, that gives you the value of B. Now, once you know B, you can find A by using this relation, right? And then for the next part of the question, you can put M and N both equal to 1. That would give you the frequency for the TM11 mode, right? So can you try solving the question now that this is given? Just a couple of minutes. Standard is simple. You know B, so you know A. Put N equal to 1 and tell me the answer. Okay, so we are trying to solve this question, and here this is a very standard question directly using the relation for the cutoff frequency for different modes. So the cutoff frequency of a TE02 mode is given. We have to find the cutoff frequency of TM11 mode given the conditions that A is equal to 2B. So based on all the conditions that are provided, what should be the answer? Can you just take a couple of minutes to solve it? Standard things, right? I think these are the typical type of questions that come in assignments. Like that's what I've seen in the last couple of years. So just getting used to the equations. And so it's very standard, right? So let us just, I'll just tell you the answer and we can get going maybe. So once you know B, A is equal to 2 into B. Okay. And then put A and B here, putting M and N as 1. And then you can get the answer. So if this is your B, A is 5, put in the values, and this is what you get, right? So that's your cutoff frequency for TM11 mode. Okay. Now, this is a very, simple and conceptual question. So You can also write in the chat box if you want. Maybe you can answer. Waveguide can be considered as. I'm seeing Tanmay writing somehow. If you have to write too much, you can also unmute and just say in case it's same time. One can also write if you. I have a doubt regarding the course that where I'll get the previous year papers. Oh, okay. So I actually don't have any idea about it because see this TA class is mostly a part of the Himalaya TAship that I'm doing. And here what we have been asked is that you just go through the previous assignment questions, like previous year's assignment questions, and try to solve similar kinds of questions, or you know just discuss the doubts, or give some idea about how to solve those questions. So that's what I know about the the question papers for the exam or something. I don't have any idea because I'm not I don't have access to such those um papers, I guess. So sorry, I don't have much idea about it. Maybe you can, if there are other TAs of the course, or you can just talk to the instructor, like the professor who directly. Maybe he'll be able to help you. Yeah, welcome. And though I did not help because I don't have any idea about previous year's questions. Okay. So for this, what should be the answer? Like anyone can answer. I think this is a very standard question. If you have doubt, you can feel free to ask me. But if you already know the answer, can you tell me? The waveguide can be considered as.
High pass filter, ma'am.
Yes. And that's because we have a lower limit to the frequency below which the wave vector becomes imaginary, the wave number becomes imaginary, and waves get attenuated, right? So it's a high pass filter. Okay, very good. Now, there can also be questions like this where, there's a tunnel is modeled as an air-filled metallic rectangular waveguide, okay? And the dimensions are given. So A and B is provided. Which statement is true? So basically, what we have to do is it's air. So the speed of the wave can be considered to be the speed of light, C, okay? A and B is provided. So what you can do is you can try to find the lowest, uh, the the cutoff frequencies based on the same formula that you have here. Okay. And then you can see whether you're in the given question, whatever you have, whether that is below the cutoff or above the cutoff. Okay. So if it is below, it would not get propagated. If it is above, it will get propagated. Right. So again, very standard kind of questions. Now, let us talk about this, which is degenerate modes. So what we saw is that when we talk about the cutoff frequencies, right? So when we looked at this expression, we saw that for a particular combination of M and N, okay, this is the form of your cutoff frequency. Now, many combination of N and M can give you the same cutoff frequency, okay? So all these are called the degenerate modes, right? So now the question says that among the following, which of them are degenerate? Okay, they are different modes, but they correspond to the same cutoff frequency. Okay, so okay, Can you take a minute and answer? What do you think the answer should be? Degenerate modes have same cutoff frequencies. Okay. So just look at the options provided, and the options by themselves will tell us what the answer should be. I would like you to answer. If you have any doubts, suppose you're not able to, like, answer or get the question, you can ask me. Okay. So just a hint is that if this is your expression of cutoff frequency, we use the same expression for both TE mode and TM mode, right? Both TE and TM have the same equation of cutoff frequency. The only difference between TE and TM mode comes in the lowest value, the lowest frequency possible. There, in one case, we have 1,0, like M1 and N0, and in another case, we have both M and N being 1. That's the difference, right? The lowest frequency is different. But for a given particular mode, the expression of frequency, cutoff frequency for TE mode and TM mode is the same, right? So now that we know that, can you tell me what the answer should be?
That option, ma'am.
Yes. So very good. So that's the answer, and this is because M and N both has to be 0, right? Because if any one of them goes to 0, the TM modes do not exist, right? So once both of them are non-zero, for a given value of M and N, whether it's TE or TM does not matter. The cutoff frequencies are the same, so they become degenerate. Okay, so the answer is third. Okay, so that's the answer. Okay. So now we'll slightly change gear and we'll talk about pulse on a transmission line. So initially, when we had discussed about transmission line, we had discussed about all these situations, right? We had a generator end, then we had a load side, and then we knew that in order to have proper transmission, we have to do a matching at the load end and at the generator end. Okay, so typically this is how your transmission line would look like. You would have some load here, and if the load does not match with the characteristic impedance of your transmission line, you would have a non-zero reflection coefficient, okay, at the load end. Similarly, if the impedance does not match at the generator side, you would have a non-zero reflection here as well. You can also have this RS, which is like a resistance at the generator end, okay. Now the question is that if you have some pulse, signal that is there at the generator end, okay, what happens there? Now you can understand, because the signal has, so when it is pulsed, it has a very finite width, okay, and based on whether you are taking longer time for your wave to propagate, whether the reflection coefficients are causing very significant reflection, your net signal that you would get at the load end might significantly vary, right? So that's why it's very important to look at and design transmission lines, or choose the lengths of transmission lines, or the resistances like the loads and everything, so that there is less distortion, there is less reflection and all that. Okay, so to understand that, let us look at this case where you have some pulse signal that is being transmitted along the transmission line. Okay, and here the reflection coefficient at both the load end and the generator end is non-zero. So that means there is some impedance mismatch. Okay, so there'll be multiple reflections that will happen. Okay, and the signals can get distorted. We'll see how much and how can we calculate that distortion. Okay, Now, any pulsed signal is something like this, right? There'll be a non-zero finite quantity for some time, for some duration t, and then it would go back to zero. That's your pulse signal. Right? So a pulse signal can be actually written as a combination of two signals. One is a constant like V naught, right? And then added to it is a signal like this, which remains zero till a certain point, and then you have minus V naught, right? So anything like from point t, what happens? This becomes zero, and this becomes minus V naught. So basically, so this is V naught, this is minus V naught, they cancel, and the net voltage turns out to be zero. Anything beyond capital T, right? So basically, now you can consider a pulsed signal as a combination of these two signals. Okay, a constant V naught or a minus V naught that starts after a time t, where t is your pulse width. Okay. So now using that, what we can do is we can try to solve questions like this, which will basically give us an idea about how to look at, what happens to the signal as a pulse propagates or transmits along a transmission line. So suppose you have some given, reflection coefficient at the load end, and there is a reflection coefficient at the generator end. Okay. There is a pulse where the pulse, like the amplitude, the voltage is given as 12 volt. Okay. And the pulse width is given as 0.1 nanosecond. You have a length of transmission line, which is given as L. Okay. And the signal is transmitting at the speed of light, given as 3 into 10 to the power 8 meter per second. And T is the time that the signal takes to, go from the generator end to the load end and vice versa. So that's the time taken for the propagation along the transmission. Okay. That's 0.3 nanosecond, right? So you would see that, the fact that here the pulse width is like 0.1 nanosecond, which is less than your TD, which is 0.3 nanosecond, is a very important point. Okay. And we'll see that this is not good. Okay. So this, as we saw, we'll see that there will be significant distortions that will come in because of this point. Right. So now consider a case where you know the reflection coefficients at both load and the generator end. Okay. And you have said that the load resistance is given as 100 ohm. Right. So if you know the load resistance and if you know the reflection coefficient at the load end, you can actually find the characteristic impedance of your transmission line, right? So basically, you had this relation. So you know RL and you know tau. So you had this relation, right? RL minus R naught by RL plus R naught should be equal to tau L. This is something which we have been discussing on the last two classes, right? So you know the reflection coefficient, you know the load impedance, you can find the characteristic impedance of your transmission line. And then once you know the characteristic impedance of your transmission line and you know the reflection coefficient at the generator end, you can also find what is your impedance at the source end, right? So if these three values like tau G, tau L and RL is given, you can find R naught and RG. RG is the impedance at the source end, R naught is the characteristic impedance of your transmission line. Now, once you have calculated that, okay, this is the typical value that would come out to be. If you have any doubt about how we are getting to this point, please, stop me and ask. Okay. So now once you know R naught and RG, okay, and you are said that there is a 12 volt signal that is coming from the source. How will this 12 volt be divided between the two? That is just a voltage division, right? So what will be the voltage that will be propagated along the transmission line? That will be given by 50 by 50 plus 25, right? Basically just voltage, it's like the voltage divider circuit. Okay, the voltage is getting divided based on the impedances or the resistances that are there. So out of 12 volt, it is this 8 volt that will be propagated along the transmission line from the generator end, right? Now, once it reaches the the load end, what would happen? There'll be a reflection, right? Because you know that there'll be a reflection which is given by this value here, tau L given as 1/3. Okay. So that tells you that if V1 plus, which is the voltage that is going from the generator towards the load, is 8 volt, what will be the reflected voltage? That will be given as 8/3, because this is the value of your reflection coefficient, 1/3, right? So now you know that, right? So accordingly, what you can do is you can represent it graphically as something like this. Okay. So what we are doing here is we are considering two straight lines. One is at z equal to 0, which is your generator end. One is z equal to L, which is your load end. Okay. Now at t equal to 0, you have this 12-volt signal that is starting from here, right? So this 12-volt pulse that you have, remember, you can write it as combination of a plus 12-volt signal at t equal to 0 plus a minus 12-volt signal after a time t, where t is your pulse width, right? So that's what we'll do here. So at t equal to 0, you have a 12-volt. So you have this 12-volt signal, right? Now it takes some 0.3 seconds to reach your load end, right? So at 0.3 seconds, what would happen? You would have a like 8 volt reaching there, right? Because V1 plus is 8 volt, right? Now, once it reaches 8 volt, what will happen? There'll be a reflection, right? A reflection which will give you what is the voltage that will be reflected back. That will be 8/3. So that is 2.66, right? That is the voltage that is getting reflected. This voltage will again take another 0.3 seconds to reach your generator end, right? Now, again at the generator end, there'll be a reflection. How much will it be? Is given by tau G. Remember, it's a minus 1/3 value, right? So that means here, if you have 2.66, you will have it multiplied by minus 1/3, right? That is nothing but minus 8/9. So that's your voltage that is getting reflected from the generator end at 0.6 seconds, right? Again, it would take another 0.3 seconds to reach the load end, right? Again, at the load end, it will get reflected by using this reflection coefficient, which is 1/3. So minus 8/9 into 1/3. That's your reflected voltage from this end, right? Now, similarly, what would happen? The pulse of 12 volt comprises 12-volt signal at t equal to 0 and minus 12-volt signal at 0.1, right? So again, from 0.1, you have a minus 12 volt, which would again move towards your load. So out of minus 12, minus 8 will be the one that will be reaching your signal, right? So if it starts at 0.1, it will reach here at 0.4 seconds, right? Similarly, if you just keep on multiplying the reflection coefficients accordingly, so here we'll again multiply by 1/3. That will give you minus 2.66. It would reach the generator at 0.7 seconds. Okay, so 0.4 plus 0.3. And then again here there'll be a reflection which is given as minus 1/3. So minus 2.66 into minus 1/3 will be 8/9. That will be propagated towards this point. It will reach here at 1 second. Okay. Then again here you would have another reflection. So again multiply by 1/3. Okay. So that's how you can keep on doing this. Okay. So based on this relation, now what this is telling you, so if you just look at 0.3 to 0.4, this region here, where your signal has reached the load end, you have given 12 volt at the source, right? But when it reached the load after 0.3 seconds, what is the signal that you are getting? So you have 8 and you have 2.66. So if you add the two, basically you are getting a pulse of 10.66 volt, right? Now it has another multiple reflection, and again at 0.9 and 1 second, like between 0.9 and 1, you would have another signal coming in. And how much will that be? So you have minus 8 by 9, and then you will have minus 8 by 9 into 1 by 3 because of the reflection, right? So when you add them, you get a minus 1.18 volt, right? So you can see, while you have given 12-volt signal, what you are getting is wildly different, and it's changing a lot in a very less, like, within 1 second, you can see what change is happening, right? So it's getting distorted quite a bit. You're not getting 12-volt at the load. Okay. And that is happening because of this multiple reflections and the impedance mismatch, and the fact that your pulse width is smaller than the time it is taking for the transmission to happen. Okay. So this is not a very good combination, as you can see. Okay. So that's how you can calculate and then use this calculation to design your transmission lines or your circuits accordingly. Okay. So based on what we have just discussed, there can be typical questions like this in your assignment, where you have this. Suppose you have a 1 meter long transmission line. So your L, the length of your transmission line, is given. Okay. Is connected between load and pulse source. You have a 20-volt source from 0 to 0.5 nanoseconds. So that means the pulse width is 0.5 nanosecond, and the so pulse width is 0.5 nanosecond, 1 meter is your length, and you have a 20 volt. So V naught, the starting voltage is 20, and tau L and tau G is provided. Okay. The load is given, ZL, RL, whatever the load impedance is given. So that means you can find Z naught or R naught, which is your characteristic impedance of your transmission line. And you can also find RG or ZG, whatever, that is the impedance at the generator end. So this two you can find from these three relations, right? These three values, tau L, tau G, and ZL, right? Just as the last question. And the speed of transmission is given. You have to find the load voltage at t equal to 3.5 nanosecond. Okay. That is how much. That's the question. Okay. Then it starts find the voltage reflected from load at some 3.8 nanosecond. Okay. Or, what is the voltage at 10 nanosecond? So if all this kind of questions that you have to find, what you have to do, you have to make diagrams like this. Right? First of all, you use these values. So similar to these questions, all the values are provided in the next question, right? And you need TD. TD is not provided here directly, but the speed of the propagation is given. So speed is given as 3 into 10 to the power 8, and the length of your transmission line is given. Length is given, U is given. So from there, you can try to find what is the time that it takes for the transmission, right? So you can find TD. All other values are provided. So for the next question, you have this as 0.5. Here you have 20 volt. This is 1 meter. This is the same speed. You can find TD. So you can follow the same procedure, try to draw a diagram like this to actually find the answer to that question, right? So that means basically for the first part of the question, the reflection coefficient at the load end is given, ZL is given. So you can use this relation to find Z naught. Again, at the generator end, tau G is given. Okay. Z naught you have just calculated. So by using this relation, you can find RG. Okay. So then at the source end, this is how your source side looks like, right? So now based on this, can you try to answer these questions? Maybe I'll give you a couple of minutes, try to solve it. It's just similar to the one that we just discussed. Okay, so I would like you to solve it by yourself and maybe tell me the answer and then we can discuss. You can take some time. You have to draw that diagram, right? Similar to the last one.
Could you proceed, ma'am?
Okay, so I would like you to solve first. That is, see, you know ZL, you know Z0. From ZL, you have found Z0, you have found RG. So at the source end, you have a form like this. So based
Yes, ma'am.
on this, can you first, yeah, tell me.
Now here power cut me, ma'am. So dark here.
Hello? Hello?
Can you hear me?
Yes, yes.
Power cut here, ma'am. Power cut. No power here now. Just I'm watching the session. I could not solve
Okay.
now.
Okay. So can you tell me what to do? So suppose here, so you have 20 volts, right? And you
Yes,
have a
ma'am.
25 ohm at
Ah,
the source end, RG,
50.
and you have
Ah.
R naught of 50, right?
So according
So
to the voltage division rule, 50 by 75 into 20 volt.
yes, so that should be something that will be propagated along the transmission line, right? So
Yes.
that will be, so if you draw, so once you draw, what would happen if you start with 20 volt? The first time, so in this diagram, the first time when it will reach here, this it will not be 8, it will be just that ratio into 20, right? Understood, right? And similarly, when you start from after 5 seconds, so basically after 0.5 nanosecond, what would happen? You would have a minus 20 volt. And then minus 20 volt will also get transmitted in the same ratio, 50 by 75 into minus 20. That's your signal that will be propagating from 0.5 to the time that is taken. So what is the time TD? TD will be given by 1 meter and then you have U, right? So basically what you have to do is when you find V1 plus, this is the ratio that we just discussed, right? So that is 13.33 volts. So you start with 20, but the first time the voltage that reaches, like the signal that is starting at t equal to 0, when it is reaching the load at 0.5 nanosecond, it will be 13.33 volt. Okay. And how much of it will be reflected back? That will again be given as 1/3 of
By 3.
this
One
value.
third.
So this is 4.44 volt. Here, now you have a transmission line which is 1 meter long and the speed is 3 into 10 to the power 8. So that would give you the value of the amount of transmission time, right? What is the time of transmission from the generator to the load? So that is given as 1 by 3 into 10 to the power 8. Clear? So that is 3.3 nanosecond. So basically here, when for this case you had it's 0.3, right? So for the next question, it will not be 0.3. This will be, so the time that you would take will be 3.3 nanosecond. Clear? So something like this, right? So you start with at t equal to 0, you have a 20 volt plus 20 volt. It would propagate. And at 3.3 nanosecond, it will reach the load where the voltage would be 13.33. Okay. When it will be reflected from this point, you would get a 4.44 volt. Clear?
Yes, ma'am.
after 0.5 second, because your pulse width is 0.5 nanosecond. So that's why after 0.5 second, you will have a minus 20 here at the start, right?
Yes. Mm.
So minus 20 into this ratio into 2/3. So that's the minus 13.33 that is getting transmitted, right? And this again will take another 3.3 seconds. So this will reach your signal at the load at 3.8 nanoseconds. Okay. So now based on this, can you tell me, here there was a question, right? What is the voltage reflected from load at t equal to 3.8 nanoseconds? Voltage reflected from load at t equal to 3.8 nanoseconds. So it's already there in your answer, right?
Minus 13.33.
No, minus 13.33 is the one that is reaching your load. So it starts from point, where is my,
0.5.
1 second, I lost my point there. Huh. Okay. So at 0.5, there's a 20 volt starting here. When it is reaching this point, you have a minus 13.33. Okay. The question says,
Yes,
what
ma'am.
is the voltage reflected from the load, right? So from the load, see, from this end, you will be having this 3 point. So anything at 3.8 second, what is happening? Minus 13.33 into 1/3, right? You have a 1/3 there. Is it clear?
Yes, ma'am.
So minus 13.33 reaches here, and then you have another 1/3 multiplied because you have tau L equal to 1/3, right? So then the one that is getting reflected is minus 4.44. Clear? That's reaching again after another 3.3 seconds. Okay. So similarly, now if you want to find what is the load voltage at t equal to 3.5 seconds. So 3.5 nanoseconds. So 3.5 nanosecond means somewhere here, right? So what is the pulse that you will be getting here? So that will be, you have 13.33 and you have 4.44, right? So you have to add the two. That's the net voltage that you are getting. That's the pulse, peak, that height, pulse height that you'll be getting at 3.5 nanoseconds. Clear? So that's how you do at different times. If you are asked what is the load voltage, you have to look at what is the net, look at all the positive, negative, everything that is reaching the load at that time period, and then try to find the net voltage, the net pulse height. Okay, that's for this part, this kind of question. If you are asked what is the voltage reflected from the load, then see what is the voltage that is reaching at that point, and then multiply your reflection coefficients accordingly. Okay, so here it would be like minus 4.44. If you're asked find the voltage at load at t equal to 10 nanoseconds, so you have to keep on doing this kind of, you reach to the generator again, then again you do another set of reflections. Okay, be careful about the fact that when you are multiplying at the load side, you are multiplying by tau L, which is 1/3. When you are multiplying at the source side, you are multiplying by tau G, which is minus 1/3. Okay, so this signature, the signs are also important. So once you do that, you have to repeat it. And then if you're asked find the voltage at 10 seconds, so that is here, right? So what is the net voltage? So minus 1.48 and 0.49. Okay, so that will give you the net voltage that you will have at 10 nanoseconds. Yeah. So that's how you have to answer this kind of questions. Any doubt?
Okay, ma'am, it's clear.
Okay. So this is telling you that, see, the values are changing as as you have multiple reflections. Here again, what you are seeing is TD, the time of transmission is like 3.3 nanoseconds, while the pulse width is much smaller, is 0.5 nanosecond. Okay. So this is not an ideal condition, right? Ideally, you want your pulse width to be much larger than the transmission time. Okay. So that in one pulse only, like you have the least distortion possible and least reflections possible, and you reach your load. Okay. So pulse width should be much larger than the transmission time along the line, or equivalently, the transmission line should be much shorter than the spatial extent of the pulse. Okay. So this is very important when we design fast circuits which involve very small pulses, very short pulses for very small time, all those kind of things. There you have to take care of this point so that you have less distortions. Okay, so if you have very sharp or very small rise time, fall times involved in all those kind of cases, you have to take care of this points. Okay, so then the transmission width the line length has to be chosen accordingly, or you have to add or change ZL or RG accordingly. So all these changes has to be done accordingly so that maybe you can minimize tau L or tau G. So you have to do all those kind of engineering in order to minimize your signal distortion. Okay. So there can be different kinds of applications of this this fact that you can have this kind of distortions and how do you avoid it. So this can be useful when we talk about high speed PCBs. So in these days when we are designing, PCBs or USBs or DDR, all those on chip things when you're doing, we want it to be very fast. Okay, so we want extremely short rise or fall times. So the pulse width are smaller. So in that case, the cables that are used to connect or the traces that are there are designed so that the pulse duration is much longer than the transmission time or the round trip propagation time. Okay. Otherwise, there'll be a lot of distortion and you will not get the signal that is expected. Okay. So even when you design transmission lines, you want to minimize pulse spreading, okay, or reflections, reduce the number of reflections. So there you have to choose your transmission line lengths or the impedances accordingly. Okay. This can also be useful when you're talking about RF or microwave communications, like when you're designing a, in rather wireless communication, satellite links, all those kind of cases, you have to choose your transmission lines based on these points. Okay. And then in many cases, when you are actually trying to test your, there can be situations where you have some device, you want to test the robustness of the device. So in that case, there's a test which is this electrostatic discharge testing. So for this kind of testing, you have, like, what one does is there can be ways of mimicking a typical discharge scenario, and for that you use pulses. Okay. So all these pulses, so in those cases you want to engineer or design pulses with specific widths, specific heights, okay, without much distortions. So there you have to have such kind of transmission circuits which cause or which minimizes the distortions possible. Okay. Even in, like, in our labs, when we are trying to test a sample, or we are doing some signaling, some sensing applications, or some test signals are involved, you work with oscilloscope. So a typical coaxial cable is a transmission line, right? And then you connect your transmission line to your oscilloscope. So if you're really talking about pulses, very short pulses, then your coaxial line widths, how long they are, okay? So those things are very important. A very twisted, turned coaxial cable can bring in new distortions to your signal, which you will not be able to understand how they're coming, okay? And they will also tweak your results and everything. So these are, when we are talking about microwave signals, very small picosecond, nanosecond pulses, or even more smaller. In those cases, you have to be very careful about how you design your signal and what is your cable length, what kind of coaxial cable you're using, what is the, the terminating impedance at the end. Okay, so all those things are very important when you design such kind of signals. And even in pulse forming networks, okay, so when you're talking about lasers, you are using pulse lasers or something, or you're using radio transmitters, different medical imaging facilities. In all those cases, if you need very precise pulse widths, you do not want pulse broadening or, very long distorted rise and fall times and all that. So there you have to be very particular about what is the transmission line, how you are matching the impedances, okay, what's the length of your transmission line, and there all this understanding, which looks quite simple, and we are just looking at the theory here, but when it goes to engineering, you have to be really very particular about it and use this concept. So these are the different applications where this ideas can or this understanding will come very useful. Okay, so yeah, that's it. Thank you. Any particular questions?
Thank you, ma'am.
Okay. Thank you. Thank you.